So hello everyone, we are team TriagePal, and today we are excited to present a solution for enhancing early medical assessments using integrated AI. Our team consists of Jeffery, Katherine, Javon, and me, Jazmine. So the global healthcare system faces a critical challenge, which is reducing the time it takes to accurately triage patients with common yet potentially serious visual symptoms like eye infections, skin rashes, or non-healing wounds. And delays here can seriously impact the patient's outcome. So our Triage Pal, the AI pre-analyst tool, addresses this directly. So we have built a robust multimodal AI agent that fuses patient input, such as a photo of the affected area and a written description of symptoms, to instantly calculate a comprehensive integrated urgency triage score. This moves AI out of the diagnostic lab and into the critical first step of patient care, providing immediate, actionable data to both patients and clinicians. To start, I will discuss the journey of this project, beginning with the constraints we've navigated and how we successfully pivoted to deliver the final product. So our project, TriagePal, an AI-powered pre-analysis tool, addresses a critical issue in modern healthcare: the overwhelming patient volume faced by emergency rooms and the resulting need for rapid, accurate triage decisions. Patients often provide limited or vague information, such as unprocessed photos or brief symptom descriptions like, "I just have an itchy arm." This can slow assessments and risk errors. So the Triage Pal is an AI-powered telehealth tool that supports triage nurses and patients by analyzing user-uploaded images, such as rashes, eyes, or even wounds, and text-based symptoms before or during an ER visit. So our goal is to deliver two key outputs: a patient-friendly summary, like a rash may need to see urgent care, or a formal clinician report. That includes triage urgency and key observations like possible infection, high urgency. By integrating computer vision, NLP, and machine learning, TriagePal streamlines preliminary assessments, enhancing ER efficiency and ultimately improving patient care. So our initial focus for this capstone was full participation in the AI Agents Hackathon, aiming to demonstrate the integration of AI agent with external tools. While we were ready to commit to this competitive structure, we encountered a significant, unexpected challenge. The hackathon itself was inaccessible, and it had passed its registration deadline. So, per our professor's instruction, we had the option to choose from three different project types. Option A was where the instructor would present the comprehensive project for all the teams. Option B, we would follow the guidelines for a student proposed project. And lastly, an industry partner project, if it was available. Our team promptly pivoted, choosing the most academically and professionally responsible path, which was dedicating our efforts entirely to option B, the student proposed project. We decided to build a comprehensive, robust triage pal, and the strategic pivot allowed us to demonstrate adaptability and integrity by focusing on the project's real-world application and solving a real problem that hospitals face daily. So we also deepened technical proficiency and focused on building the core technical pillars promised in our proposal: computer vision for image analysts, NLP, which is natural language processing, for symptom parsing, and lastly, machine learning and deep learning for accurate triage scoring. Now, Jeffrey will introduce you to the resulting final project, our Triage Pal, the AI agent.
Thank you, Jazmine. So, following our pivot, we developed TriagePal into a multi-model AI agent built to address the core triage gap by combining different data streams for comprehensive assessment. The core functionality of the TriagePal has two primary inputs: a visual image, which is a photo of a body part like an eye, rash, or wound; patient symptom text, which is a description of their condition. Our system processes these inputs and generates two clear outputs, which is a patient summary and a detailed clinician report. Crucially, featuring an integrated urgency triage score, low, medium, or high, so you can get a complete understanding of the severity of your symptoms. The three pillars of multimodal AI. To achieve the intelligent assessment, TriagePal relies on the seamless integration of three distinct AI components, which is the computer vision component, the CNN. This module, based on a convolutional neural network, processes the uploaded image. Our initial work focused on binary conjunctivitis classification, but we extended this to classify multiple conditions, including skin rashes and wound types based on combined data sets. It determines the visual category and confidence score. The second is natural language processing component, the NLP. This module analyzes the patient's symptoms, description. Instead of simple keyword matching, we employ sophisticated techniques like BioBERT, which we'll discuss shortly, to extract symptoms and objectively quantify a symptom urgency score. And the third is a decision agent component, which is the random forest. This final machine learning model fuses the outputs of the first two pillars. It takes the multi-class visual probability vectors and the quantified symptom urgency score to generate the single definitive triage score that informs the final clinical recommendation. This layered architecture ensures that TriagePal provides a robust, data-driven, and highly reliable initial triage decision. So Katherine will now walk us through how these three technical pillars were developed and implemented.
Thank you, Jeffrey. I'll now detail the technical core of TriagePal, how we built and integrated our three AI pillars to create a unified system. Our visual system began with a focused CNN for binary conjunctivitis classification. Our early prototype achieved a test accuracy of 83.33% on the eye dataset after 30 epochs. To create a genuine triage pal, we had to expand this beyond eyes. We gathered diverse data, combining the initial conjunctivitis images with datasets for skin rashes and wounds. The final CV model uses a customized convolutional neural network architecture that includes three convolution 2D blocks with max pooling and batch normalization for stability. The image input size is 128 by 128. This model's output isn't a single class, but a multi-class probability vector, indicating the likelihood of the image belonging to each potential condition, for example, eye, rash, or wound, and their subcategories. The second component tackles the symptom text. Instead of simple keyword spotting, we leverage the power of BioBERT, a language model pre-trained specifically on biomedical text. Symptom extraction: BioBERT uses its deep understanding of medical language to identify and extract relevant symptoms and entities from the patient's text. We use a simple weighting scheme to assign an initial symptom urgency score based on key markers like redness, swelling, and pain. The NLP component outputs a quantified score and the number of symptoms detected. This gives the system a structured understanding of the patient's reported feeling, not just the picture. The third pillar is our final decision layer, the decision agent. This is a trained random forest classifier. It functions as the crucial bridge that fuses the two modalities. It receives the CV probability vector and the NLP features, urgency score, and symptom count. The output is by training on combined image and symptom feature sets. The random forest model learns the complex patterns that link a specific visual pattern to a specific symptom set, ultimately predicting the final triage urgency score as low, medium, or high. The combination of CNN-based image feature extraction and BioBERT-based symptom extraction provides the robust features needed for the random forest to make a reliable, integrated triage prediction. Now, Javon will take you through the complete system flow and how we ensure data persistence and ML ops monitoring for a professional deployment.
Thank you, Catherine. The real power of the TriagePal is how these three components integrate a clean, professional flow and how we handle persistence and model tracking, preparing this for a true production environment. The TriagePal system flow. The system operates as a data pipeline with clear stages. Input acquisition, the user uploads an image and enters system's text via streamlit interface. Multimodal feature extraction, the image is processed by the CNN to yield a visual probability vector, and the text is paraphrased by BioBERT to yield qualified urgencies and system count features. Intelligent triage decision. These merge features are fed into the trained random forest classifier, which predicts the final integration triage score, low, medium, or high. Reporting. The system generates the patient's summary and client's report based on this final score. For any clinical tool, data logging and auditability are non-negotiable. This is where persistent layers come in. We use an SQLite database to log every analysis performed. The database Sigma records clinical information for each assessment, including the raw image path and system text. The system determine CV class and prediction confidence. The final prediction triage score. Example, it could be high, medium, or low. The timestamp and the final reports for audit purposes. This structure ensures that every patient interaction generates an audible record, clinical for healthcare compliance and retrospective quality checks. Finally, our development wasn't a single run. It was a measured process. We leveraged ML flow throughout the model development phase. ML flow allowed us to automatically track the thousands of hyperparameters tested during our const tuner search, compared dozens of experiments, and logged artificial artifacts like our final optimized model weight. Our final triage agent and key metrics such as MOC, AUC, and K's kappa. This ensures our project is fully reproducible and transparent, fulfilling the mandate for robust development and documentation. With the technical, artificial detail, the team is ready to show you the application in action. Now Katherine will show us a live demo.
Thank you, Javon. So for this part, we will be actually pulling up an example of our application, the TriagePal, on our GitHub repository, so you guys can just see it action and work. Jazmine, I'm not sure if there's a way you can make my screen full screen so they can get a good look at it. But here I will share my screen and I will upload an image and give an example of the symptoms and conditions, and we'll see what processes. So I will let Katherine explain from here. Is everything good? Can you guys see everything?
Yeah, it looks good.
Okay. So here I upload the image.
Oh,
on the
you're muted, Catherine.
First
So
for
here
our
okay, it's all good. It's okay. So here I upload the image, and now I am about to input a description of the symptoms and conditions, which is I have a serious redness and intense pain in my left eye started 2 days ago. As you can see, the file is uploaded of the picture of the eye. And here I will hit analyze, and I will let Katherine take over from here.
All right. And so yes, first we'll simulate a user uploading an image of an infected eye, as we just did. Next, we enter the symptom text. I have a serious redness and intense pain in my left eye, started 2 days ago. When the user clicks Analyze, like we just did, the system immediately triggers the entire multimodal pipeline. Next, behind the scenes, the CNN processes the visual data. The convolutional layers identify features characteristic of conjunctivitis, generating a medium probability score for the infected eye class. Simultaneously, the BioBERT NLP pipeline extracts keywords like redness and pain and assigns a combined symptom urgency score of 2. The random forest decision agent then receives these merged features, the high infected eye probability and the medium symptom urgency score. It integrates this data and makes its final prediction. The symptom immediately generates the reports. The predicted triage score is medium. The patient summary is clear. This condition appears to be medium urgency. Consult a doctor soon. The clinician report provides the necessary audit trail. Triage score medium, CV prediction, infected eye, symptom urgency 2. Finally, look below at the recent analyses section. This is direct evidence of our SQLite database integration, the new record, complete with the time, the CV class, and the final triage score, has been successfully logged for compliance and retrospective review. This showcases TriagePal's ability to provide a fast, integrated, and fully logged pre-analyses, acting as a true intelligent agent in the triage process. Now I'll hand it back to Jazmine for our conclusion and future outlook.
So, in conclusion, as you can see, the TriagePal successfully fulfills the central educational objective of this capstone, which was building a sophisticated, functional, and auditable AI agent. We successfully created a multimodal triage system that intelligently fuses image data from our optimized CNN with textual symptom data from BioBERT and NLP model. The system delivered a single reliable urgency triage score using a random forest decision agent, moving beyond simple classification to integrated clinical support. We implemented a robust, persistent layer using SQLite and MLOps workflow using ML flows, ensuring every analyst is logged and every model is traceable and reproducible. Crucially, we turned an inaccessible assignment requirement into an opportunity for deeper learning, demonstrating adaptability, integrity, and strong teamwork. Looking ahead, we see clear paths for the TriagePal's evolution. We can expand the model by integrating additional disease models, moving beyond the current eye, rash, and wound classes to cover even broader scopes for dermatological or ocular conditions. We can also develop API hooks to connect the clinician report and triage score directly into existing electronic health record systems, automating patient intake and workflows. We can also advance the triage by incorporating non-visual patient data, such as age and medical history, into the random forest model to further refine its predictive accuracy. We are really proud of what our team has accomplished, turning our challenges into successes, and we are now open to welcome any questions you may have. Thank you.